recording. All right. So I did have a few people come up and say, hey, there's assignments up there, but you haven't said anything about that. That's true. Sorry about that. But I did change the due dates for those. Let's see here. I'll just take a screenshot. How about throw them in here? I bumped it to Friday. That felt as good a day as any. Let's see here. Yeah. Whenever we finish a concept, then I give you a week to do the assignment on it. Okay, I often forget to mention it. Pretty bad to forget in the first week or so, first assignments. So sorry about that. But in general, you'll have a week to do these assignments, unless we're coming up on a test and I want to make sure that you do the practice with the assignments. So the practice before the test, then I might have to scrunch things up a little bit. But in general, you'll have a week's go around. Okay, and there's also assignment 3 posted. And when is that due? I'm in student mode, so I can't enter it, but I think it's due on Monday next week. I'll check. Yeah. Oh, now I did it. Oh my gosh. That's bad for me. Okay. Oh well. And assignment number 3, which is on numerical data or summarizing numerical data. Is, data is due, I want to say September 25th. Did anyone catch what it was? Is that right? Thank you. And all my due dates are at 11:59 at night, because midnight gets confusing. Then you have a less, anyways, whatever. 11:59. And I'm also, so why is it due next Monday? Well, because we finished numerical data last day on Monday, so then I give you a week. And it's not up yet, but you'll also have assignment number 4, which is for categorical data, summarizing categorical data, which will be due, we'll finish it today, so it'll be due next Wednesday, which is what, September 27th? Give you an idea. All right. A little bit of review, but we did finish the section, so but it'll come back to haunt us anyways, so may as well review it, but we don't need it necessarily today, so just a quick recap. Okay. We landed on the shape of the distribution determines the appropriate measure of center and spread, right? And so shape determines center and spread, or the appropriate measures of center and spread. So if you have a unimodal symmetric distribution, right? If the shape is unimodal and symmetric, right? And I'll throw the word normal in here because we'll start seeing it in chapter 4. We hold off until then, but that's what it's going to be called. And I'm going to give myself a little bit more room bumping this over here. Then the center and spread that we can use, or the best center and spread. If we have a unimodal symmetric distribution, then we can use the mean and the standard deviation. Write it all. Wait, one line. Oh my gosh. That's if we have a unimodal and symmetric distribution. And if you have a skewed distribution in any way, then you should be using the median and the interquartile range as your center and spread. That's not to say that you can't calculate the mean and standard deviation. It's just saying that they're not appropriate measures of center and spread anymore. Okay. And I'm going to capitalize this mean here because it looks weird if I don't. So we talked about, well, IQR is what? It's the interquartile range. IQR, the distance between the quartiles. So it's Q3 minus Q1, which leads us to kind of recapping the 5-number summary, which is the minimum, Q1, the median, Q3, and then the maximum, right? Chopping our data into quarters. And so we also talked about the median, which is the value that splits the data in half. And I said, okay, if we're going to be doing these things by hand, then you would just have a small data set, right? What are some things you're going to do? You're going to sort the data from smallest to largest. All right, so step 1, sort. Step 2, patent pending, boop, 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 method in, right? Don't worry, I don't have a patent pending, but I think it's funnier when you say that. Right, so take your fingers and you boop, 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 boop. And then if you land on 2, what do? You take the average of the 2, right? And then boop your way into the middle. All right. We're not gonna do those today because we did them last day, right? And they take some time. And then the quartiles do the same thing, but now you're focusing, you're basically finding the median of the lower half and the median of the upper half. Do the same thing, but with the lower and upper half. Of the data. You'll see in the, if you didn't have a lab on Monday, might have a lab with me today. And then we're going to use Excel to find quartiles and medians and things like that, right? Which was kind of unfair to the ones who are in the other section because they hadn't seen any of those on Monday. Very confusing. So it goes. Okay. So we'll use Excel or some sort of software to find these things, but it's good to know, you know, what it's doing, although it gets a little fancier than what we were doing. Okay, call that end of the review. This is section 2.2. So we spent a lot of time summarizing numerical data, and that's kind of where I started off at the beginning of the course saying, okay, numerical data is very interesting. There are a lot of things that we can do. And in terms of categorical data, there really isn't a lot that we can do, right? What's one of the things that I said we could do for categorical data Well, now we have categories. I can look at counts in the categories. What if I want to level up just the hair? Well, I could look at a contingency table. A contingency table considers two categorical variables and how they relate to each other, right? Or some sort of relationship. So here, right, I might have variable number 1, and then here I might have variable number 2. Doesn't matter which one's 1 and 2, but so here, right, notice that inside the table we have counts, just like we were saying, but now these counts are kind of from multiple categories. And so here we have the distribution of students' genders and whether or not they're looking for a spouse while in college. How do we get this data? I don't know. Probably made up. So, and I will say this, in all of these examples, we're limiting to just 2 genders. I recognize that that's not necessarily true, but it makes our questions a lot simpler. So we've got that at least. So if we just consider males and females, and then whether they're looking for a spouse, that's a yes or no question. Well, it's deeper than that, I know, but in this case, yes or no. What if I find the right one? What if I don't? Conditional statements. All right. Let's just take it for what it is. It's just an example of a contingency table. Okay. So now we've got counts, but what does this 86 tell us? It tells us that out of a total of 207 students surveyed, 86 of those were female and not looking for a spouse while in college, I guess. Right? And so now we can find the proportion of students that satisfy some criteria, which is also going to translate into probabilities later. Okay. And so as a brief example, and let me just, no. For example, 86 out of 207 students were female and not looking for a spouse. So this 86 out of 207 makes it a proportion, right? So we're going from counts, so raw counts, to proportions. And then, so here, this is a proportion. But later, and by later, I mean later today, we're going to see that proportions are probabilities. Which are roughly percentages. I have to multiply by 100, right? And so, which are roughly percentages. Notice that you've got P, P, P. So all these 3 P's, you can use them interchangeably, just like the average and the mean. You can use them whichever one sounds better, right? Sometimes it sounds better to say mean. Sometimes it sounds better to say average, for example. And so proportion and probabilities are between 0 and 1. Spoiler alert, I guess. And then percentages are between 0 and 100, right? Just multiplying by 100. Okay. But that's way too big of a peak forward, I think. Let's just stick to what we've got. Okay. But that's something to keep in mind, is that those 3 P's mean the same thing. All right. Time How many females did we survey? 137 of the 207, right? So we can extract a lot of information from the joint counts or the marginal counts. I don't call them that, but so I'm not going to write it down. This might be too much. But how many of the students were looking for a spouse? 69 out of 207, right? They were looking for a spouse. I didn't specify what gender, so then 69 out of 207. So there's a lot of things that we can extract from this table, and we'll be working with it later. Okay. In terms of visualizations, we don't have a ton of options, or I should say we don't have a lot of good options. And so for visualizing categorical variables, usually what we're stuck with is a bar plot, right? Or some version of a bar plot. This is different from a histogram, and notice that there are two different bar plots here. This one has just the raw counts on the axis here. So here, I call them raw counts just to emphasize that they haven't been manipulated. Whereas here, I have the proportions, or the proportion, I guess, on the y-axis. The graphs look the same, right? It's just when we look at the relative frequency bar plot, which is when you have the proportions on the axis, then it just shrinks it down to a scale of 0 to 1. Okay. But the graphs look the same. And if you're not careful, right, you might mix this up with a histogram, but then you'll see, oh, actually, I have categories here, right? And so that's what makes it a bar plot. So here we have categories on the x-axis. So similar to a histogram, right? But the x-axis determines that they're very different. Right? So that's the most basic visualization that we have for categorical data is a bar plot. Now we can get a little bit snazzy with this if we wanted to. We could not do that. I'll come back to that slide, sorry. But I'd already segued into this one. We could have stacked bar plots, side-by-side bar plots. This is if you have more than one variable, right? Standardized stacked bar plot. So what these look like, just some examples. And we'll play around in Excel in the lab next week, right? Playing around with some of these graphs. It proposes kind of suggested graphs that you could use. So we'll just play around with those, but notice, right, regardless of the graph that you use, you've got a categorical variable on the x-axis, and then here we've incorporated another variable by splitting up the bars into categories, right? And so got a couple of options. And there's also this kind of, I think this is a mosaic plot. That's how often I use it. I don't really remember, where the width of the bar showing that there's fewer, right? So the total area would be 1, but we just let software do that. It's not something that I care about terribly. Oh, here's more mosaic plots. Okay. Let me have a sneak peek. Yeah, okay. Now I'll go back to that slide that I skipped, because I already had the other one lined up. Okay, so we're back to this contingency table, right? And so the question is, does there appear to be a relationship between gender and whether the student is looking for a spouse in college? Now, I guess I shouldn't be there. There, giving it away. How would you think about this? So you would look at the difference between, if there's any, in the proportion, okay, fine, in the proportion or the percentage of females looking for a spouse versus the proportion or the percentage of males looking for a spouse. Now, so what we're seeing here is that 51 out of 137 females, right? There were generally more females surveyed. So we need to take that into account, right? And so 51 out of 207 is not going to take the female aspect into account, right? And so that's why we need to do 51 over 137. And so we get roughly 37%. This is wrong, actually. Duh, I'll use red. This should say what? Proportion. That's me being picky, but it's true. Or I could have said 37%, right? 0.37 or 37%. But how it was wrong. Versus males now 18 out of 70. So we sampled fewer males, that's fine. And we only found 18. So raw counts, obviously way less, but we sampled fewer people. So in order to compare the two, right, we need to convert to proportions or percentages. And so we find 0.26. Now, right, or, oops. 26%, if you prefer, right? This is where it gets a little bit into some gray area. If I asked you, well, 26% versus 37%, some of you might say, yeah, that's a big difference, right? And some of you might feel like, no, that's not really that big of a difference, right? Maybe they're close enough. Meaning what? If my argument is, no, they're relatively close, then what am I saying? That there's no apparent relationship between gender and whether the student is looking for a spouse in college, right? If you're telling me that, okay, that's quite a large difference in percentages, then what are you saying? Then you're saying there appears to be a relationship between gender and whether the student is looking for a spouse in college. Now that's really difficult, right? 26 versus 37, and it's all about how you feel about it. That's not good, right? We want hard rules, and we will have them, but generally that's what we're going to be doing, right? So not there yet, but we will have ways of determining if there's a relationship or not. Okay? But at its core, this is just what we're doing, just comparing them. Okay? I personally would say that there is a relationship, right? In fact, it looks like females are more likely to be looking for a spouse in college. I know. Unbelievable. Paint us into a corner like that. Or men aren't. Either way. Oh yeah, mosaic plots here. You've seen them. I don't care about them. Pie charts. Are you ready for a rant? Don't use pie charts, okay, guys? There's one thing that, well, hopefully I'll teach you more than one thing. But if there's one main takeaway, is if you ever reach for that pie chart and you're tempted, you say no. Why? It's hard to read. Exactly. So yeah, so here's an example, right? As soon as you have more than potentially 2 categories, right, it becomes difficult to read. You can't see which slice is smaller and which one's larger. And that's the whole goal, right, is to be able to visually communicate information. Okay, and so pie charts, I don't know how they got so popular. There was also a season of the donut chart. Are we still into donut charts? Where you cut out the middle? It's an option in Excel, I'm sure, still. They released that probably, maybe, time flies when you're having fun, right? Maybe 10 years ago. But so they were all the rage. No, 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 I don't want to see it. The only time, but all right. I'll take a moment. The only time, oh, that's fine, that a pie chart is obvious is if you only have 2 categories, right? But if you only have 2 categories, right, then you could just communicate that with one number. You don't need a graph, right? If I tell you, oh, the proportion of people who pass this class is 90% or 0.9, you know that, 10% don't? Oh my gosh, right? You understand from one number what the other number is going to be, right? And so that's the problem. And that's why I posted that video, which is probably not going to play. Am I going to be that cool and play it in class? Force you to watch it if you haven't watched it? Is it going to work?
Surrounded by killers?
You don't think people in this store do marijuana, do you?
I mean,
Probably.
I can't raise it.
How many of them?
Like half.
Half. Wait, half do or half don't?
It's both.
Both?
okay.
Anyways, and let's remember that that was me standing in front of my TV trying to get it. That's how important it was to really drive this point home. Okay, and so here I'll say pie charts are only obvious, right, in terms of reading them, understanding them. They're only guaranteed to be obvious when there are only 2 categories, right? Half do, half don't. Categories. But in that case, we can communicate with one number instead of a graph. Just writing down what I said. I could just say 90%, or I can draw a pie with a 90% slice and a 10% slice. But, okay, maybe that was a bad pie chart, but doesn't matter. All right. Any questions about that so far? All right. So what if we do a mashup? So now I'm looking at numerical data. So one of my variables is going to be numerical, and then across groups, which means I have another variable that's categorical. Okay, and so here one numerical variable and one categorical variable. There are other options for looking at this mashup, okay? But one of the most used versions is this side-by-side box plot. I'll put it here, side-by-side box plot, even though I think the name is pretty obvious from what it is here. Okay. So what do we have? Does there appear to be a relationship between class year and number of clubs students are in? So the number of clubs is here. I guess that's your numerical variable, and then the categorical variable is year of school or something like that, where we're looking at 4 categories, right? What have we done in terms of our data set in a spreadsheet, right? You might have one column with the number of clubs that the student is in, and then another column with what year of school they're in or class year. I don't know. I never understood the sophomore, junior, senior thing, but someone could explain it to me, that'd be great. But it's okay, I get it. So now you have all the students in one spreadsheet, and you've got one column of the number of clubs that they're in, and then one column with these categories that they're in. Each one's only in one category, right? Be pretty weird to be in 2 categories. And so all it's done, right, is it's looking at little subsets. Everyone in the first year, well, here's their numerical data. Everyone in sophomore year, well, here's their numerical data. I guess I should use this. Junior year, same thing. Here's their numerical data. And then senior year, here's their numerical data. What it allows us to do, though, is it allows us to compare things like the medians, right? The median is at the thick line, right? And so here, if I compare this median to this median, basically the same, right? We allow some wiggle room. These are probably small data sets as well, which gives us more freedom, right? We're not going to be as picky for small data sets. Even this one, if I had to talk about this median compared to the other 2, well, I would say that it's roughly at the same place as the 3rd quartile, right? Meaning what? Junior year, they're in typically more clubs than first year and sophomore year. Okay? And then senior year comes along, and I have to assume that that's when you get busy. And then you're back to relatively the same number of clubs on the median, not on average, but median, right? And so we've also got some whiskers, we've got outliers in the sophomore and the junior years, right? So it helps to be able to read these box plots. And so you can do things like, what's something interesting here? Nothing interesting is jumping out at me. Usually there's things like this one. Imagine that I'm dragging it. Oh, you can't see it. Hey, fine. What if I bumped it up to there? So ignore this bottom one. Then what could I say? I could say that all of the data for the senior years are higher than even the whiskers for the sophomore and the junior years, right? It's just looking at how these things compare. It's nothing crazy. I'll delete that. Generally, if I had to generalize this graph here, I would say, looks like the distributions are approximately the same for all of the years, right? Approximately. There's some wiggle room. And then, of course, a pie chart of your favorite bars and a bar chart of your favorite pies. It doesn't make sense though. I hate to poke holes in this, but you can only have one favorite bar, right? Favorite. I guess, yeah, it doesn't make sense, but that's okay. How would you accumulate this data? It can't be my favorite bars. It would have to be our favorite bars. Then we have a categorical variable. Our favorite pies, because you need more than one data point, right? But I still think it's funny. All right. That's where we stop summarizing categorical data. We're going to see categorical data quite a bit, obviously, but in terms of summarizing it, there's not a lot that we could do or even want to do. And so that gives us a good toolkit. Any questions about that before we start the next chapter? Woo. All right. Now, I am going to, I posted the chapter 3 slides, but it was just before class because I found something I had to fix, but that's okay. Confession time. I don't like probability. But once we're through with this section, we're going to be having so much fun. But we do have to get through this chapter. I called it section. It's a chapter. It's a whole chapter. And if you don't like probability, then it's my fault, and I apologize in advance. How I feel about it rubs off on you. Or maybe you love it so much that you want to take a course on probability, game theory and stuff like that. That's all probability. Chapter 3 is called what? I think just probability. What gets confusing, especially in later parts of the course, is we're constantly going to be talking about probabilities. What's the probability of this? What's the probability of that? Right? Given the probability of this, what's the probability of that? Okay. But it won't be in this sense. Okay, so this is kind of a strict probability section. And so we're constantly talking about probability, but this is a special case, I guess. All right. So probabilities come from random processes. Now, if it wasn't random, then who cares? You would know what was going to happen, right? And so the only time that we need probabilities is if we have this random process. So a random process is when we know what outcomes could happen, right? Which means that we have some sample space where we can list all the possible outcomes and we have a good understanding of what could happen, but we don't know which one will happen. Yeah. Things like tossing a coin, rolling a die, iTunes shuffle, I guess. Whether the stock market goes up or down tomorrow, right? That kind of thing. We understand it's going to do one of those two things, right? It can hold steady, I guess, but minute changes, right? And so we understand it's going to do one of those things, but we don't know which one, right? And so there are cases where we're gonna talk about a process as if it's random because it helps in terms of finding probabilities when it's not actually random, but that's just a side note. All right. Probability rules of the road. So the number one rule for a probability, and I already said it and I'm skipping ahead, I guess, is that a probability has to be between 0 and 1. Okay? Just like a proportions between 0 and 1, percentages are between 0 and 100%. And I guess what I should have introduced is this probability notation. Probability notation, where you use a capital P and then of A to denote the probability of event A. So A is some event, and it has some probability of happening. And this says, and this is the most important thing, probabilities must be between 0 and 1. That's the number one thing to keep in mind. So yeah, fine, a little rant. In statistics, there are kind of two streams, and the kind of traditional one is a frequentist, and I would say I'm a frequentist. Sorry, I'm not like the cool kids, the Bayesians. So a frequentist says, okay, well, if I were to see this random process happen, then over an infinite number of times, what's the probability that something would happen? So when we say, okay, I'm going to flip a coin, let's say it's a fair coin, right? Nothing funny about it. Then I flip a coin and I know that it's a 50-50 split, right? The probability of heads is 0.5 and the probability of tails is 0.5, or at least that's what we assume. I think they landed on, there's a slightly uneven probability, and I know it could land on the thing, but we ignore that. Then we topple it, right? Or just wait for it to fall. Right? But what have we done? We've pretended to observe it an infinite number of times, and then over time we would expect, if there are 2 outcomes, a 50-50 split, right? If there are 3 outcomes, a third, a third, a third, right? That kind of thing. Whereas the Bayesians, and these are the cool kids, and I don't know, for some reason I can't get there in my mind, but I can't get it to make sense to me, but so a Bayesian just says, I'm going to assign the probability of flipping a head 0.7, and then they just make adjustments as they see more outcomes. To me, that's weird. That's a weird way of doing it. It's the cool way of doing it, but still. Ideally, you pick a value that's close to the final value, right? And you have some understanding of it. But anyways, it even claims here, oh, it says it's true. It is popular now. But just in the recent kind of 20 years, because we need computers to be able to run simulations and things like that. And that's how we adjust our probabilities, right? So we say, I'm gonna say it's a 70-30 split for flipping a coin. And then you run a simulation and you say, oh, I actually had to adjust that, right? kind of backwards. All right. Which of the following events would you be most surprised by? Exactly 3 heads in 10 coin flips, exactly 3 heads in 100 coin flips, or, oh my gosh, 3 heads, exactly 3 heads in 1,000 coin flips? Well, the most surprising, I'm gonna go ahead and say is that one, right? Exactly 3 in 10, I'm fine with that, right? That seems reasonable, okay? 3 in 100 is weird, but not compared to 3 in 1,000, right? So what we're saying is with the law of large numbers, hard to say, as we observe more observations, right? So as we observe more coin flips, like I said, seeing 3 in the first 10 is not that weird, right? But as we see more coin flips, right, we expect the proportion to even out around 50-50, right? Because there are only 2 outcomes. Okay, and so in general, what that graph ends up looking like is if we have a line here at 0.5, then we might, for small coin flips, if I have the number of coin flips, it might be super volatile here, but as it increases, it starts hovering around a 50-50 split, right? If I only flip it 20 times, it's a reasonable outcome that I only see 1 tails, right? And the rest are heads. Right? But if I do it 200 times, then it starts to even out, right? And so that's kind of just a very poor visual representation of the law of large numbers, right? So as you increase the number of occurrences, then you converge on the overall proportion, the true proportion. Okay. So here I'm going to put P hat, and then here we have P. Now, the reason that I am using this notation is because we're going to see it later. And so it's good to have seen it. We don't have to worry too much about it now, but P hat is the sample proportion. Whereas just a P is going to be the population proportion, or percent. No, I don't want to talk about, but probabilities. But I'll say proportion, right? P's are all the same. Proportions are probabilities. And I guess I should have said probabilities because we're in the probability section. This is where, I think we have probably done enough work to understand that, okay, well, if I flip a coin, right, each coin toss is independent of the next. But it's still easy to get caught up in, oh, well, I mean, you flipped this many coin or flip this many heads. How could you possibly get an 11th head here? So when tossing a fair coin, if heads comes up on each of the first 10 tosses, right, then what's the probability or what's the chance that you get another head on the next toss, right? And it's important to recognize that all those flips, they're all independent of each other, right? So it doesn't matter how many you've seen, right? And so I'll highlight it. The probability is still 0.5. Even if you've seen 100 heads in a row, the next flip, same probability, right? And there's a lot of kind of interesting things that we could say about this. For example, if I got you guys to just simulate your own head toss or coin toss, right? Head, tail, head, tail, head, tail. It'd be very easy to see which ones were human generated and which ones were actually simulated, because we reach this point and we say, well, I can't, it has to be tails. I can't do this anymore because it's random, right? But that's how they catch counterfeiters and stuff like that. And so that's kind of an interesting thing, is our human inability to actually do random things, right? We think we're doing a good job, but we're not. Okay. We are going to be using probability notation quite a bit. So in terms of reading something like this, right, it's just a condensed way of saying, and you can write it in a sentence if you want, but that's going to get really tedious really quickly. And so how we read this is, bless you, the probability of, right? So when you have those brackets, then you read it as of. So this you read as the probability of, and then whatever's on the inside, ahead on the 11th toss. On the 11th toss. Just in terms of reading that probability notation, which is going to be the same as the tails on the 11th toss because they're independent events. It's that gambler's fallacy. All right. Is it roulette where you get caught up thinking, well, I mean, we've seen that so much already, it couldn't possibly, and then it does? Well, it can, with the same probability as when you started. And so, right, the law of large numbers, right, it's easy to misunderstand it, but what we're talking about is, and I want to put it maybe here, tossing a coin is an independent, independent event. All right. Each coin toss is independent of the previous and the next. Can't see what time it is there. So let's talk about disjoint and non-disjoint outcomes. So disjoint or mutually exclusive outcomes are things that cannot happen at the same time. For example, if you flip a coin, right, there are two possible outcomes, but if you flip it once, only one of those two things can happen, right? And so they're disjoint or mutually exclusive. So here are some examples. The outcome of a single coin toss cannot be a head and a tail. A student cannot both fail and pass a class. It's one or the other, right? And so, and then a single card drawn from a deck cannot be an ace and a queen because you only drew one card, right? So these are all disjoint outcomes. When they cannot happen at the same time. As opposed to non-disjoint outcomes are things that can happen at the same time, right? So now I'm considering things that could happen jointly. A student can get an A in stats and an A in econ in the same semester. You're not just limited to one A, right? You're allowed to have multiple A's, right? And so then those would be non-disjoint outcomes. However, there is some probability of getting an A in stats and some probability of getting an A in econ, right? And so, and there's some probability, some overlapping probability of getting an A in stats and an econ, right? Probabilities. So usually when we talk about non-disjoint events, we introduce a deck of cards. And this is where I get, I don't know cards. I don't know cards either. But there are some key things that we have to remember or that you can easily look up. But things like there are 4 suits and there are 13 cards in each suit, right? There are 3 face cards. And what else? Half of them are black, half are red, right? And so there's all these kind of things to keep track of for a basic deck of cards. And I only mention that because there might be assignments, questions, I can't remember, where I get you to answer questions about a deck of cards. But then you can just pull this up and have a look. Yeah. Okay. What's the probability? Well, how many total cards in a deck of cards? 52, right? Phew. Okay. I'll write that down. 52 total in a deck. We'll start there. Okay. So what's the probability of drawing a jack or a red card from a well-shuffled deck? Meaning, they're not stuck together or anything. They're just random. Okay. So if I break this up, I want to draw a jack. And I'm going to try to match these colors here. So now I look at the outcomes out of 52 that satisfy being a jack, right? And so I have 4 of those. So what I can say is the probability of a jack is 4 out of 52 cards. Okay. So far, I think it's pretty reasonable. A red card, confusingly, they used blue to circle the red card. Okay, fine. What's the probability of a red card? 13 and 13 makes 26 out of 52. What's the problem here? Nice. Nice. These 2, I've counted twice. So in terms of our calculation, right? Yes, you can just add up these probabilities, but if you've counted some overlap, then you have to subtract the overlap, right? And so what it kind of devolves to is the probability of drawing a jack or a red, right? I don't care which one, just one of those 2 is going to be the probability of a jack plus the probability of red, but then minus the overlap. And here the and is the most important part, right? So you have to subtract the overlap. Subtract the overlap since it was counted twice. Fractions, right? adding, subtracting fractions, you have to have a common denominator. So I would just encourage you to leave it as 52, right? Or make it 52 if you can, right? And then you can add and subtract in the numerators, right? 4 plus 26 minus 2 puts you at 28 over 52. Or if you have all possible outcomes, 52 of them, couldn't you just count them? You just go through. This is a jack. This is a jack. 1, 2, 3, right? This is a jack and red, right? You could just go through and visually count them. That's not always going to be the case, right? But you can confirm that we have counted 28 cards there, right? Which makes sense. You have 26 in the red and then 2 more on top of that. And that's how you get to the 28 over 52. Okay. So you could just look at it, see what things satisfy the criteria, and then you're done. Right? But having this kind of a formula to work with, and we will establish the proper formula, but it doesn't look like it's on the next slide, so we'll hold off just a little bit. We could have a contingency table. And so what's the probability that a randomly sampled student thinks marijuana should be legalized or they agree with their parents' political views? And so those are our 2 categorical variables, right? They share their parents' politics, yes or no. And here they want to legalize marijuana, yes or no, right? Only 2 possible outcomes in each. We could have more, but makes for a bigger table. It kind of makes a mess. And so what did we want to do? We wanted to find the probability that a student thinks marijuana should be legalized or they agree with their parents' political views. So here, in terms of, so here, these are the folks who think legalized, yes, or they agree with their parents' political views, which would mean that they're in this category. Now, the problem with just adding up the totals here, right? First, I got 114, and then I got a total of 118 out of 165. But what have I done? What have I done? I counted 78 twice, right? So you'd have to extract that one time. Yeah. And so here, so here, whether they agreed. In terms of notation, I can say the probability of L or agreed, kind of getting ahead of myself in terms of notation, right? But just stay with me, is going to be the probability of L legalizing it, which is 114 over 165, right? Plus the probability of A, which is agreeing with their parents' political views, which is 118 over 165. But then I have to subtract that overlap. How am I going to talk about this overlap, this 78? Well, those are the people who think that we should legalize marijuana and they share their parents' political views. So that's going to be the minus the probability of L and A, which I need more space for. because it's important. So here I have 114 out of 165 plus 118 out of 165 minus 78 out of 165. Math. I'm gonna go with this one. They didn't even do the math. Just went for it. Because you've got a common denominator. Cat. Need common denominator. Right. Just as a side note, that's more of a math note, not a stats note, but they run together. So what we have established is called the general addition rule. So the general addition rule says that the probability of A or B, notice that now I'm allowing for any two outcomes, A or B, right? A, B is going to be the probability of A plus the probability of B minus the overlap, right? A and B. So here, what are we doing? We're subtract, bless you, subtract the overlap. The special case is if you have disjoint events. So if A and B can never happen together, then the probability of A and B must be 0, right? And so the special case is when A and B are disjoint, then you might have something like this, right? Or at least that's how I think about it in my mind, right? A and B can never happen together. So then the probability of A and B must be 0, right? There's no shared space, which would denote the overlap or the probability of them happening together. So then you have a special case where that's when you're allowed to just add the probabilities as long as they can never happen together, right? This is another way. So if you flip this on its head, how I would use this is if I wanted to prove that something is disjoint, right? Then I could start by saying, okay, well, then the probability of A and B must be 0, right? So I tend to flip it on its kind of opposite direction, I guess. We often use things called probability distributions. They're just a table of the possible outcomes and then the probabilities of each of those outcomes happening. Okay. So the probability distribution for the gender of one kid, isn't that a baby, is that a baby goat? Right? So way cuter if we think of it that way. There'll be male with a probability of 0.5 and female with a probability of 0.5. Okay. Now there are rules for probability distributions, and one of the things that I often ask, you know, on test 1 or whatever is, which one of these are the appropriate probability distribution, or which ones are a possible probability distribution. And what that's doing is it's making you go through this checklist, right? And make sure that everything is satisfied. And there will be some that are not satisfied, right? And then you'll be able to eliminate and figure out which one is which. So the rules for probability distributions. First of all, the events listed must be disjoint, right? If there's overlap, then you can't list the probabilities and it just doesn't make sense, right? So that's number one. Number two, each probability must be between 0 and 1. That goes back to just probabilities in general. It's not a probability if it's not between 0 and 1, right? And so, of course, any probability that you've listed has to be a probability. So that's fair game. And then the probabilities must total 1. Why? Well, I had to list all possible events. If I've listed all possible events, then if I add up all those probabilities, one of those is going to happen. I just don't know which one, right? And so that's why the total probabilities has to be 1, right? Since and I'll kind of clarify that here, since we list all possible outcomes, right? One of those things has to happen. We don't tend to do probability distributions for something this simple, right? But we could do it for something a little bit, well, it's still pretty simple, but a little bit bigger, right? What if we have 2 kids? Is it kids or kits? If we're talking goats. I feel like it's kids, right? Yeah, right? Never doubt yourself. What are the possible outcomes? First one, so remember I have 2 of them now, right? First one's male, second one's male. First one's male, second one's female. First one's female, second one's male. First one's female, second one's female. And now I've run out of options. Male, female, male, female. The probabilities are just going to be spread evenly. What have I done? Or what have we done? We've taken a total probability of 1, right, and spread it across 4 possible outcomes, right? So here, and that's often how we arrive at probabilities. Take a total probability of 1 and spread it across 4 categories, obviously evenly. You can use the fact that the total probabilities has to be 1 to find missing probabilities, right? Even if this one, if this one wasn't given, you would say, okay, well, I mean, they have to add to 1, so the only thing missing here is 0.25, right? And so we rely on that fact that we have a total probability of 1 quite a bit. This one's kind of tricky, I guess. But in a survey, 52% of respondents said they're Democrats. What's the probability that a randomly selected respondent from the sample is a Republican? Now, there are kind of a couple of answers, right? Why? Well, are those the only 2 parties? Or are there more parties, right? If we assume, so let's start there. If we assume that there are only 2 parties, then what's your answer? We're gonna go with 0.45 or that would be confusing, 0.48, right? Because you're not a Democrat, you are a Republican, assuming there are only 2 parties, right? And so here, assuming only 2 parties. What if there were more than 2 parties? Then which option would you have to go for? Remembering the fact that it can only add to 1, right? And if we're, so 52%, they're Democrats, right? That's fixed. And then now we have to move over for another party besides the Republicans. So it can't be more than 0.48, right? Because that's if there was only 2 of us, right? And so now it would have to be less than 0.48, right? Oops. If there are more than 2 parties, right? So I guess ultimately the answer would be, can I calculate using only the information given? Because it depends on which one, but those are your 2 options, right? Which I think is more helpful. All right. Okay, just one more, because I've said the word sample space already, so it's time to introduce it. But then there's also some questions that you can work on for Monday. Crazy. So the sample space is going to be the collection of all possible outcomes of a trial. Flipping a coin, you've got heads, tails, right? In terms of gender of children, let's just assume male, female, right? Otherwise, you'd have to list many more combinations, and it makes it harder. Yeah. So the sample space is the list of all possible outcomes. We already did it, right? When we had a look at, okay, 1 child is either male or female. No, 1 baby goat, 2 baby goats, right? We listed all the possible combinations, right? That's the sample space. And so here I leave you with these questions, and we'll pick up there on Monday. How about? If you have any questions, let me know. Otherwise, have an awesome week/weekend.